I want to start off with things that we've already seen in the lab, because one of the things I like about the way Tipler goes through Lenz's law is he starts with, he says, this is experimental fact, and then he goes from experimental fact onward. Because remember that scientific theories start from observation, and then they must, whenever they come up with the actual theory, it must predict what will happen in real life, or it must at least follow what we have seen in real life. Now, when we did Ampere's law before, and we found the fringe field, we used Ampere's law to prove the fringe field inside of permanent magnets. That was the same idea. They didn't start with Ampere's law and say, hey, I think there's a fringe field. They could see that from iron filings, and therefore Ampere's law, which is trying to explain the real world, must account for that. And so by using that example, we were able to say, see, Ampere's law is still valid, even in this case where there was no current whatsoever. Okay? So going back to first basics, we have our galvanometer here, and we have our magnet, and as we know, we saw that as we moved a magnet, now right now there is a magnetic flux, there is magnetic field inside the solenoid, but there's no current. Why? Because it's not changing. We also know that if I go slowly, we get a little bit of magnetic field, a little bit of current, and if I go quickly, we get more. Now, we could take the time to talk about what we did in the lab, which is called Lenz's law, which says that it opposes, right? So that if I put a north in, it produces a north out trying to stop it. We're all good with that. So we know from fact, from observational fact, empirical data, that a changing magnetic field and eventually a changing magnetic flux causes electricity. And of course, electricities come from voltages, which we call EMFs. Now, other things that we should know: if we have multiple, lots of things over here that are metal. So in this case, I have different solenoids. This may or may not be big enough. Let's see if it'll go through. And notice we get a little bit here, more, and you see how that pegs it, right? Okay, so we have now seen that more coils equal a stronger EMF. Yes, we're all in agreement with that. So whatever theory we come up with must account for, it must be moving, and that's where we got per time, right? Over time it changes, and it must account for the number of loops. Now, another example, here's a generator that works by changing magnetic field by turning this. I will get a current in the light I was supposed to have. It was working earlier. Is it not on at all? Yeah. There we go. Okay. So, if I go faster, it gets brighter. So again, how fast I turn it, we get a greater EMF as well. So it's also dependent on changing by changing the angle in some form. Okay, changing velocity, changing angle, etc. As the change increases, the EMF increases. Yes.
Yes.
I don't think this one is as useful. It's fun to watch, but not useful. And then here, I've got a couple of paper clips here. I've got a solenoid. I put electricity into it. Right here, notice it says DC, and we know that DC stands for direct current, which means it's going one direction. And we can see that there's a magnetic field because it picks up the paper clips. Okay, and when I put this into another coil, I get nothing. Now, is there still a magnetic field? Yes, there is. But they're not connected. We can see that they are not connected. However, if I change it over to AC current, will there still be a magnetic field? There is, and if you listen carefully, you can hear it buzzing, which is the 60 times per second that it switches forward, then backwards, forward, then backwards. I put it inside here, and now we get a magnet. Now we get current in the other coil. Reason being that this one has a changing magnetic field, not just a magnetic field. This is no different than me taking the little solenoid that we had and being able to move it in and out 60 times per second. So according to what we have seen, we are absolutely certain of a few things. If the magnetic field changes, we get a current or we get an EMF. The faster it changes, we get more EMF. The more loops there are, we get more EMF. We're all in agreement with these facts. Okay. Now, the way that this is, let's again start from basics and we're going to build into that. EMF is defined as work per unit charge. It is not, even though it is joules per coulomb, remember that it's not voltage, that's the general term. Potential difference is joules per coulomb as well, but it is not work per unit charge. Potential difference is potential energy per unit charge. And EMF is what gives that potential energy. So this is defined as work per unit charge. Well, what is our definition, our big boy definition of work? F dot dx. And then of course that's over Q. I'm going to take the Q in, and what's F over Q? Newtons per coulomb is electric field dot dl. Now, we came from our basic definition. This is the most important thing of what you just saw. That EMF is defined as work per unit charge. And then we just followed the white rabbit. Okay? Now, the next thing that Tipler adds on this, he says if you have a closed loop, then it equals this. Next, we have found out that EMF is produced when there's a change of magnetism. And we found out that we could change if we changed area, we changed magnetic field, or in the past we found that if we take the coil and we change its direction, which is actually what's happening with this thing. I'm actually not changing them, I'm not moving the magnets, I'm actually taking loops of wire and I'm spinning the wires. And as the wires are spinning, the angle is changing. And so here we get this equation. d dt of the magnetic flux. And Justin, if you'll just make sure that if I move to the side that, yeah, you don't have to, if I'm on the edge, I'm okay, just as long as it's not like, yeah. The negative is, again, Lenz's law, yes, which says that it opposes the change. That's the, putting a north in, it makes a north out. That's the example of Lenz's law. Now, those of you that were observant of what we did on Maxwell's equations, I'm going to build the next step from basics. This next step is what dogged me for about 3 hours, and I've got it now. That this, so now we have one definition, we have a second definition. This is Faraday's law, yes? With Lenz's law embedded. Now we need our definition of magnetic flux. Magnetic flux is defined as that's an S. That's what we're here to talk about. Yeah, John Michael's over here smiling because he and I talked earlier today. Did you read about this some?
Yeah.
This is a big deal, isn't it?
Yeah.
So what Tipler talks about is that if we had some area, an easy area, if we just had a circle, and then actually he does a triangle of sorts. That if you were to take, say, you've got some sort of surface, and you've got the magnetic field or an electric field, right? Flux could also be an electric field flux. So we can see that we call this right here dA, and this would be B. And you can see in this case, when you do your dot product, then all of those lines go through that area. If I were to tilt it, not all of the lines would go through, would they? Or another thing he shows is what if I did this? And I used that area. Wouldn't the flux be the same? The area is bigger, but the flux is the same. You also see, though, that dA is now this direction, and there's a theta. Now, just to make this simple, let's say that this right here is 60 degrees. We all know where I'm going with that, yes? So, if these fluxes are the same, then this area must be twice as big, because the cosine of 60 degrees is 1/2. And of course, as theta goes to 90 degrees, the flux through the area would be 0. And as the flux goes all the way down to here, again, assuming that the field was bigger, you would get twice the flux. If the field is the same, but the area is bigger, you would get no difference. Okay? Now, if we take this area, instead of it being a large area, and we had some sort of weird shape, and each one of these were some weird little area, but we make them become infinitesimally small, then our area can become d area, which is infinitesimally small, and the smaller you get, would you agree that that would become, you could break up even a curve into flat surfaces? And that's where the integral comes from. And the S reminds us that we're doing this over a surface, but there's not a circle, as we have seen with Ampere's law and with Gauss's law. The circle means over a closed surface, and this is just a surface. The closed loop integral of V dot dl equals the time derivative of the magnetic flux, which is B dot dA. Now that's a lot of junk. Now all of it little pieces should make some sense. But I'm going to point out something that I felt really stupid earlier today, thanks to John Michael. I was talking to him about it, and it just kind of dawned on me as I was saying, as the stupid words were coming out of my mouth. Now, generally when we see a derivative and an integral, they do what to each other? Cancel. They cancel each other out. This one is dt. This one is d. They don't cancel each other, Murray. Yeah, now I feel really stupid. Okay? Now, can I show you where that kind of got me dogged, and then once I saw that, I'm totally good. Now, it turns out, remember that when we have an integral, if it's a constant, it can come out of the integral, yes? So, if we take this entire thing here, let's say that we have a constant magnetic field. Well, if it's a constant magnetic field, then we have the B can come over here, and actually it can come all the way out, can't it? So we get negative B ddt, and now we get this of the little dAs. And what is the integral of all the little dAs? A. But there's one trick that I think I can just show this on my computer, not have to turn on the Justin, can we see that?
Do you have a charger for this also? It's about to die.
I do. Can you see that?
Yeah.
That's a soap bubble on a coil. I tried to do that in class, but I didn't figure out how to do that quickly. So with a soap bubble, didn't we see earlier that there were, the more coils, the more EMF we got? Because as we talked about earlier, ladies, gentlemen, as we talked about earlier, each piece of the wire produces an EMF. And if there's more loops, you get more EMF. So what they did is they came up with this idea of a surface. The soap bubble makes a surface that connects all of that. I want to go kind of to basics and then move away from basics. We had an instance earlier this year where we were calculating voltage, and I was like, but we know that when we're spinning, we saw in the lab that when we spun a coil of wire, we saw that if you did it slowly, you saw that it went from 0 to maximum to negative to maximum, etc., right? So it actually does depend on the angle. Now, we should all know that this equals what?
Velocity.
Speed.
That's the average velocity.
Wow.
You already see what's about to happen? So therefore, this equals my instantaneous velocity. Likewise, is my average EMF, and therefore, d phi dt tells me my EMF instantaneous. Now again, when you look at it this way, your brain goes, duh, but there's a lot that you can learn by just going back to the absolute basics. Okay? So when you're doing this, if all they give you is this angle beforehand, this angle afterwards, and they ask what's the EMF, what are you really finding? You're really finding the average EMF. Okay? You want me to show you real quickly? This is actually to show you the notation. We'll do other examples as well. But watch this. This is actually from the following chapter where he goes through and he says, let's imagine that we have a coil, okay, and the magnetic field's going in a particular direction. That would be, and we are actually turning the coil, okay? It's actually rotating with time. And I guess we'll just say that there's several loops, okay? That's really not that important. Well, putting in what we know. Our EMF will equal negative ddt, Lenz's law, Lenz's law, Faraday's law, of B, which will be a constant in our case, and then dot dA. The area of that loop is actually the same, isn't it? The loop is not changing, so it's just A, and what does the dot product always give us? Cosine of theta. But we're not going to use theta, we're going to use, because it changes over time, we're going to use omega t. Let's take out our constants, etc., okay? So now we get negative ddt, constant or variable? Constant. Constant with respect to dA. We are not taking the integral with respect to time, are we? So that comes out. Woohoo. That got me badly the other night. I'm trying to figure out how to do this right. So now, this is where I'm still trying to find the best way to talk this to you. If we call that dA or just A. This says sum up all the A's. You're like, but I already have A. I've already summed up all the little dA's. Oh, but there are multiple loops. Remember the film? So this times this gives me NA. This probably would help you out. If we did this,
yeah.
That helps.
So while I was working last period, I changed it to n times dA prime, which dA prime would be the area of one loop.
It's the same idea.
Yeah.
So here we're going to add up all the little areas, right? Well, in our case, if we have a bunch of areas because of the spiral again, because you've got multiple loops, we want all of the areas be the area of each loop all added together. Okay, Aiden, do you now see how cosine of omega t is a variable here, is a constant with respect to dA?
Yeah, but right. Yeah, like when t changes.
It does, but that's where you have to do it here. Okay? So, now that we take all that in account, we get our EMF equals negative, and I'm going to take the B out, and guess what this is going to be? NA, which according to DT is a constant. So I'm going to get N, B, A, D, DT of the cosine of omega t. But that is a function of t, so I can't pull it out, can I?
Nope. No.
I could out of the integral, because the integral was with respect to dA. This makes so much more sense now. So, and what's my derivative of cosine? Negative sign. So that becomes a positive. And I have to bring out an omega, don't I? Omega sine omega t. Now, would you agree that at certain positions, the sine of omega t will be 0 to 1? So, if we want to know E max, our EMF max will be NVA omega. Now, let's see if that makes some sense. If I increase the number of loops, does the EMF increase?
Yeah.
Yes. If the magnetic field that I'm spinning it in increases, it would? Bigger area. Would I have more flux? Yes. And as I spin it faster, do I get more EMF? This, we should have no issue with this equation. And why is this the max? Because the max sign can be is 1. And what will the minimum be? 0. But if we knew how fast it was spinning, and we should remember that omega equals 2 pi over t, where t is the time for one complete rotation, then we know any given time and all of these other variables, we will know it's what? Instantaneous EMF. Simple enough. Okay, once again, here's big deal. This. No, I want to do this. So this equals that.
Yeah.
But this equals that.
Whoa.
No.
No.
What we're going to do now is just work some of the examples from the book together. And then I've got some in the actual back of the book where I not only worked the problem and then I added a step that I think will be useful. Okay? So first one here we're actually going to work is example 30-2. And instead of reading all, now, as we are starting to learn in this class, we really don't care about all the blah, blah, blah because the units will set you free. So all I'm going to do is write down the information because that's all we really need, don't we? So all we need is the pertinent stuff. So we have 30 degrees, magnetic field, 300 turns, R equals 4 centimeters, and we have this. That's enough information, isn't it? What is that? I heard someone say it.
Tesla's per second.
Say it.
Tesla's per second.
No, not you. There it is. Yeah. Not you. You. Yeah. It's dBdt, isn't it?
I thought it was
Okay, so are we all good here? Yes?
Yeah.
Go. Pause, and we'll come back. Okay. Now, since we're looking for the magnitude, can I just get rid of that? Because we're just looking for the magnitude. Almost always, it's just finding the magnitude. It was kind of nice to have the negative, though, when we did the cosine becoming negative sign. That was kind of helpful. And this is going to be and actually, yeah, so it really just kind of comes out to be this.
NBA.
Right?
Yeah.
Okay, the n will come out, the a and the cosine of theta will all come out. And what's left is dB/dt, which we have a number for, don't we? Yay! 300, and that'll be pi. I'm not even gonna put that there, but we know that that's gonna be 0.04, right?
Yeah, sure.
And that's gonna be the cosine of 30 degrees, which is what, 3/2?
Yes.
And that's gonna be 85, and the number comes out to be 111.
Yes. 0.005.
Now, we need some discussion here. Someone make a comment about that.
It's a cool number.
In this case, I think that's true. But generally, when we get to this point, don't we generally say that, oh no, because it's actually dB/dt, it's not delta V delta T, so that's the actual number. It's a constant voltage, it's not the average.
Yeah.
Do we all agree with that? Yes?
Yeah.
Okay, and the B is actually, it's a constant here. Why is it a constant here?
Because you can just take it out of the integral.
Because this integral is with respect to dA, not dt. So we get, I know that's funky, but, so we get d dt of b, I guess I could have taken the a all the way out, right? No, we're gonna leave the dA there. Cosine of theta, and then we get this,
DA.
What is the surface integral of dA? NA, which is not irrelevant. That's gonna come all the way out.
Wait, what? I'm so confused on the whole, like, taking out the B, no, it's not constant.
Because this is where A is the only variable. B is not a variable for, B is a constant with respect to A. T is a constant with respect to A. But once we get to this point, we are defining the surface integral dA as NA. Because remember the soap film. Okay, this accounts for all the ends in the coil. And so now we can just, are we right? We can all plug this in now? And I'm just doing this. dB/dt is going to equal IR over NA cosine theta. Enough said? Do I need to mess with this anymore?
Do you need the cosine theta?
No. What's that?
Do you even need the cosine theta there? Because it's not any of your variables.
Oh, yeah. So I guess this actually becomes 1, doesn't it?
Yeah.
Yeah.
You know what, that makes sense.
Are we all good?
I think you just switch these.
Okay.
No, I know, we switch them around. They get not B.
Now, let's get into a little bit stranger stuff here, just real quickly, because we're just kind of following what he has here. What about this stuff right here? If we have a changing magnetic field, or a changing flux, we get an EMF. If we look at this right here, let's assume that we have remember we had that dB/dt where it was changing with a constant changing magnetic field, right? Therefore, would you agree that the EMF would be a constant number? Go ahead, open it. Go ahead. Yeah. Would you agree that if all of this gives me a constant number, that would be 120? It would be some number, yes?
Sure.
Well, let's look here. Would you agree a certain distance from this changing magnetic field, the electric field is probably a constant? But this, if you chose a circle, would change its size. So let's imagine that we have a small area right here where we have a changing magnetic field. But I call this, well, let's call this R, right? And we could call this little r1, we call this little r2. Well, if we find the changing flux, the changing magnetic flux, d phi dt, wouldn't we have an EMF? Yes? Which says that the EMF here, the EMF at R2 must be the same, yes? There's no changing flux out here. The only changing flux is right there. However, isn't this bigger than that? Other way around, sorry. Isn't it? No. Yeah. Is it? Yeah, okay. So isn't this is a bigger circumference, yes? So the electric field here will be less than the electric field closer in, because changing magnetic fields cause EMFs. Well, EMFs come from electric fields. So changing magnetic fields cause changing electric fields. But the farther away you are from the change, the electric field is smaller and smaller and smaller. We don't need to work that problem, it's in the book. Okay, but do we follow what just happened there?
Yes.
Okay. Now, I want to talk about this a little bit more. When you see that, instead of it just becoming this, we are hopefully you are getting closer to convinced that that equals that. And all we're counting for is what? The number of loops. But not always. Because, here we go. Time to get something fun. We're going to be back in the actual problems. And this is number 10 in the problem set. Chapter 30. It gives you this. It gives you a wire with a current I flowing through the wire. Then we have a small loop over here. There's A and B, and he calls this distance from here to here D. That's the distance the loop is from the wire. Find me, and I would like you to try this on your own first. Find me the magnetic flux in this loop of wire. Pause. So you should know that magnetic flux equals, yes? That's enough. So, first of all, in order to find the flux, don't we need the magnetic field? And what's our magnetic field from a current carrying wire? So now we have equals to the integral of the circuit is mu naught I over 2 pi r, where r is the distance from here to here. And isn't that changing? And so dA, sure would be nice if we could get dA as a function of r. Do that. This. At any given r away, there'll be a small strip here. Matter of fact, an infinitesimally small dr. But b is going to be constant, won't it?
Yeah.
So it turns out that dA will become b dot dr. And what is that dr going to go from? From where to where? From d to d plus a, or a plus d, or da. Da, not duh, that's me. Okay, on. So you should see, I'm not gonna do the next step, I'm just gonna put, in, don't we see a bunch of, you can figure out what crap to take out, yes? So once we get, this is gonna go from d to d plus a, mu naught I, 2 pi r, b dr, finish it up. The crap, for those of you on the internet, that's all a constant. And now we are left with a very simple integral that, you know, and oh, there's a b there, sorry. Dr over r. And we know that the integral of 1 over r is just natural log of r. I'm going to ignore all that stuff for a bit. So this is just going to give me the log of r evaluated from d to d plus a. Can I do this in one step? Does everybody know what happens with a negative? Yes?
Yeah.
This will just give me the final minus initial. Anybody got an issue with what I just did, or is that, we're all good, yes? So now let's put it all together, and we get equals mu naught IV over 2 pi, the natural log d plus a over d. Now, before we instead of self-congratulating ourselves here for a bit, this is an important problem because it shows us that the calculus actually does work in this example. That we had a changing area, or I mean that the area, the flux changes. And so that integral actually will matter. Okay, that the integral S dA is not just going to always be NA. Sometimes there will be an actual calculus function that you have to use. Now, what we just found the magnetic flux. What did we not find? What's the EMF in that small loop? What?
The flux isn't changing.
It's not changing. It's a constant. Everything in there is a constant. However, let's just say, man, let's say that I changes as 4r squared. Let's say that t equals 2 seconds. Find me the EMF, go. A very simple problem. Duh. So instead it's supposed to be it. Okay, ready? How about now we pretend that the current is changed at 4t squared. Find the instantaneous EMF at t equals 2 seconds. I even thought I didn't work it out. But what if you're saying, now, how would you do that? Well, let's imagine you had a rheostat, which is a variable resistor, and you were able to go from 100 ohms down to 20 ohms or something like that, and you did it in a certain amount of time. If you knew your change of ohms per second, you could work out how fast your current changes. The question was, how did we get from here to here? That's the question. Well, if we look here, you can agree that as the radius is moving out, the flux, or the amount of magnetic field at each one of those points is increasing. Or it's decreasing, sorry, right, because you get farther away. But would you agree that this distance is irrelevant? Moving up and down does not make a difference, only out and in. Therefore, B is irrelevant. And so we take a very, very small dr. Remember, the dr, again, is infinitesimally small. So that we can make a little dA out of a very thin strip of this coil. And that thin strip will be dr times B.
So just the big A would just equal AB, and since B is constant, you just took the B out, and then you changed A to a variable because you can.
You could do that. You could call it that. Sure. So now let's go ahead and finish this off. Can I remove this? Okay, I need the space, and sometimes the world gets cluttered. Never seen that before. Okay, so we know that our EMF at sometimes t. Can I do that? You guys know what I'm talking about. Our EMF at sometimes t will be ddt. I mean, I don't want to do this. I don't want to start at that point. I'm going to take the crap out. So let's get rid of all the crap. We got mu naught b log of d plus a over d 2 pi. Did I get them all? Yeah. And then all I'm going to have left is ddt of 4t squared. And can everybody do this now? You can take the derivative of that, which is just going to be, so here we go. So this is going to become 8t, and we're going to put in 2 seconds, so it'll actually give me 16. Multiply all that by 16. Everything else is already given. In other words, if these were actual numbers, yes? If each one of those variables were actually given a number, you have the function for I, you were given some time t, you could find the instantaneous EMF. How are we feeling about this? 3-4. The problem is written as you've got a region of magnetic field with a radius of big R. I guess let me write these so that you can see them a little bit easier here. So if we call this outside distance from here to here, we'll call that R. And then what about in between, like somewhere less than the radius? That we'll call that R1, and out here we'll call this R2. We're talking about a circular, in all directions, right? The magnetic field is changing dB dt. Find the electric field at R1. Find the electric field at R2. Okay, we ready? Let's be working on this a bit. So we use our equation up here, and there's our electric field, isn't it? Okay. So now for A, we have closed loop integral of E dot dl, which is going to equal, and I'm going to get rid of the negative because we're looking for the magnitude, ddt of, and this is going to be B dot dA. Notice the dot products are going to cancel because it's perpendicular to the page, yes? We understand what I'm doing there? And I think it's only one loop. Yeah, so we're going to imagine it's one loop. So here, if we take the same radius all around, can we agree that E would be a constant? We're going to take E out. And what's the closed loop integral of dl at a particular radius r? 2 pi r1, which is going to equal, the b is going to come out, and we're going to get that dB dt. Why can the b come out? Because it's not, a is the only variable, b is not a variable of a in this case. And what is this? Sorry, there's an S there. What does that equal?
An A.
But there's only one loop, so it's just going to be A. But how much is actually changing? Just that much. So it has the same radius as the other side. So this side is going to be dB dt, and this is going to be pi r1 squared. And what do you notice? One of the r1s cancels. see here, John?
Mm-hmm.
Okay, so E is going to equal, the pi's cancel. I'm going to get R1 over 2 dB dt. Now in this case, as R1 increases, E increases, but only until it gets to
Two.
R, because you're still capturing magnetic field. Once you get past there, let's see what happens. Okay, got it right. It's always good to check. And then part B, now we're outside. And this side is going to be the same thing, isn't it going to be? And then it's going to be 2 pi R2. Do we agree with that?
Yes.
But on the other side, we're still going to have the dB dt, aren't we? But what is this going to turn into? How much of this has magnetic field in it?
Pi big R squared.
Pi big R squared. So that, my electric field, the pi's will still cancel, very sad. And we're going to get big R squared over 2 R2 dB dt. Does that make some sense? Now let's see what this says. Here, when we're inside the magnetic field, getting a bigger R means you get more magnetic field, more electric field. But as you get outside, you see how it's constant and constant? As R gets bigger, when it's outside of big R, the electric field gets smaller. Now what we have seen here is that as you change the magnetic field, you get an EMF, sorry, you change the magnetic field, you get an EMF. And an EMF means you get an electric field. But as you get farther and farther and farther and farther and farther away from the changing magnetic field, the electric fields that are being created reduce.
So then, as
Louis, would you please, we'll worry about that some other time, we're recording right now. Quiet, please.
if you were to graph that, would it be linear and then it would drop to a 1 over R?
Yeah, we could do that. So inside it would look like that, up to a particular number, and then it would go down as a 1 over R.
Okay.
We good? Last one, this is another one that I didn't do last period, so, by the way, there's one problem that he does, 30-5, which is pretty interesting. He has what he calls a charge collector, current integrator. And you can actually, because again, when we get this, that can turn into IR, yes? These are just permutations that the board can throw at you. If this is IR, what does I equal?
dq dt.
dq dt. So if I needed to solve for Q, I could do some stuff, couldn't I? I could throw this T to the other side, and what do you see? The T's might cancel. The DT's might cancel. Okay, next example. Example 30-6. So he gives us his magnetic field. Etc. And then he puts a coil in, he puts a wire into it. This wire is 30 by 20. I didn't do it very well, but we'll get closer. Good enough. And couldn't we change these to something else? We could call this W. Do we call this like L? Do we agree with that? Or if we call that Y, you call that X, yes?
Mm-hmm.
Okay, would you like X or W, or do you like X or Y?
X and Y.
X and Y? That actually will tell us something here in a bit as well. Delta X and delta Y, yes? Then he says we have 80 turns, and I'm going to keep that just because, remember, because one of our big things today was the notation, right? So the more times we see that, the better. And then we have our dimensions here. It's in a magnetic field of 0.8 Teslas. And he says, blah, 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 the resistance of the coil is 30 ohms. He says the coil moves with 2 meters per second squared. Yeah, now let's talk. So if we were to take this coil and we were to pull it down, everybody on your own figure out the direction of the magnetic field, or the direction of the current. You should have gotten clockwise. There's two ways to do this. If you take the right-hand rule on this, because it's moving down, right? Magnetic field in, the wires moving down should feel a force that direction, which pushes it around this direction. Using, good? Lenz's law, as it moves out, is the amount of magnetic flux increasing or decreasing? Decreasing, so it strengthens it into the board again, which causes a clockwise flow. Okay, so now let's do what we know here. What is this going to become? We're going to find the current. So that's going to become IR. So we're going to have IR, and then over on this side, we're going to have DDT. And the magnetic field as a constant is going to come out, right? So we get B, and now we have, and what is the surface integral of dA? NA.
Nate.
And those are both can come out of this, can't they? Well, no, actually, so B comes out, oh, sorry,
B's already out.
So we get B and, ooh, and what is A?
Area?
Actually, A is what?
Area inside the magnetic
Isn't
field.
it X times Y?
Yeah.
So this, someone go close that door back there, please. Since we're recording. Would you agree with that?
Yeah.
Okay, so now we get IR equals, the B comes out, the N comes out, DDT. So now we get NB DDT, and that's going to be X first times Y. If I'm moving it downward, which one stays constant?
X.
X stays constant and Y doesn't.
So it's
Do you agree with that?
d by dt, which is 2 meters per second. That's
Jack, are you in advance?
Do we see it? And what is dy dt?
2 meters per second.
2 meters per
2
second.
meters per second. Woo.
Do we see it?
Yeah.
That's pretty cool, isn't it? Now, what if we moved it this way? What would the current in it be?
Sorry?
If we move it left or right, what would the current be?
dy.
Why is that?
You do d.
Why, Jack?
It's parallel. Or, like, the flux isn't changing.
The flux isn't changing because both of them are moving that way, and they would both feel a force upwards, wouldn't they? Now, what if it passes out of the field eventually? Once it passes out of the field, what would be constant?
The
Y would be constant,
and then
but X would be
changing.
varying, and
Yeah.
so dx dt would still be
2 meters per
2
second.
meters per second. How are we feeling about that?
Good.
So real quickly, let's use the idea that we just had. And let's derive our other equation. So we have our EMF equals ddt of B times A, and notice we said A was like length times width, right?
XY.
Length times width,
Yeah.
or whatever we want to call it. Let's say that the length is constant, so I get BL. And what would, again, I guess your X would be better, right?
Mm-hmm.
And what is dx dt?
Average
That's
velocity.
just velocity, isn't it?
Yeah.
So now we get BLV, which is one of our equations.
Oh yeah. F equals or E.
Which is actually derived from Lenz's law. Or sorry, from Faraday's law.